for putting this conference together. So I'll be telling you about this integrability of the boundary Liouville conformal field theory that I've been working on with Morris Ang, Shin Sun, and Tunan Zhu. So let me start with a slide of physics to motivate this problem to explain to you what is Liouville theory. So it started out in physics in the 80s as a theory of summation over 2D surfaces developed by Polyakov. In a more probabilistic language, it's going to tell you what is a canonical random surface, what should it look like. So throughout this whole talk, I'll be working on the unit disk. And so say you write the Riemannian metric tensor of on this disk as in diagonal form. So Euclidean metric times a positive function, which you write e to the gamma phi. Gamma is just fixed parameter in 0, 2. And phi will be a random field that's going to give the law of your random geometry in a sense. And so what physicists do is they prescribe this law of phi, the Liouville field, by a formal path integral, which is a summation over all maps from the disk to R of some uniform measure times a Boltzmann weight of some energy functional. So what do we have in this energy functional? You have the most basic term you can put in any energy functional, which is this first here, just you integrate over the disk the gradient squared. So this is just kinetic energy, right? If you have only this term, then you have a free field theory. The law of phi is just law of Gaussian free field. Then Liouville theory is more complicated because you have some non-trivial potentials which correspond to, you exponentiate the field and you can integrate it then, this exponential term, you can integrate it over the disk or over its boundary. This is a boundary integral of the exponential on the boundary. And so to tune the strength of these potentials, you have two constants, these mu's. Red will be the one for the area measure, mu in red, and the mu boundary, mu b in blue for the boundary. In most generality, these two constants are positive. Okay, so now what are the observables that physicists can solve? They can solve these correlation functions in principle, at least. What are these observables? There's a sort of joint Laplace transform of your field at different points. So choose some points Zi in the disk and Sj on the boundary of the disk with some associated weights, and you define this observable, okay? And so in probability, you can view this as some, joint Laplace transform. If you compute all these functional, it's definitely gonna describe the law of your field. Okay, so now this first slide was physics, it was not rigorous probability, so I'm not gonna introduce the objects in probability that are gonna allow us to make it rigorous. The first thing we need is just the Gaussian free field X on the unit disk. It's a logarithmically correlated with this covariance function. Has infinite variance at a point, so it's actually not defined pointwise. It's defined as a random distribution. And this poses some problem when we want to exponentiate this field. So we want to exponentiate this field to define this Liouville potential that's in our energy functional. So formally, we want to define e to the gamma x, this formal density against the Lebesgue measure, see on the disk. And to do this, there's a well-known procedure now, which is some regularization, renormalization. You smooth your field at scale epsilon, divide by some term, and then it's well known this converges to a random measure that's independent of the smoothing procedure. So now when we write these formal notation now correspond to the universal object coming from this limiting procedure. Now with the Gaussian free field and its exponential defined, this Gaussian multiplicative chaos, the exponential, right? Now we can define rigorously what was on the first slide of my talk, which was, first slide was physics, now this is probability. And what you're doing is you're replacing this, this formal path integral, you're replacing it with just an expectation over the Gaussian free field. So you have this expectation here is over expectation over Gaussian free field, right? And you see you put in your expectation this product of the field at different points we're trying to compute. And then here you have the remaining part of your energy functional, which contains these two Liouville potentials, right? These two Gaussian multiplicative chaos measures integrated both over the disk and over the boundary. There's also this integral over C is called the zero mode integral. It's over an average of the field. I don't have time to get into it, but I could answer a question on it. So with this definition, yes, there's one more thing I need to say is that we also have the freedom to choose the constant on the boundary, the blue constants. You can actually choose it to be piecewise constant between different boundary insertion points. So a typical correlation is represented by this picture, right? Where we choose here on this picture, I have, for instance, 2 bulk insertions, 3 boundary insertions, a red parameter mu for tuning this interaction in the bulk, and then some values for mu on the boundary, tuning this interaction on the boundary. So the interest of studying this is really twofold. First interest is you're making rigorous, one of the most important theories in the most important conformal field theories, the Liouville model. You're studying it in a mathematical framework. Second interest is you're going to be able to import tools from CFT, the probability, to prove some facts on some probabilistic results that would be out of reach or harder to prove otherwise. So as the simplest example of this, let's do this, because the functional previous slide was pretty complicated, but let's simplify it a lot. Look at this picture over here. I'm making these choices where I'm just putting 1 point in the bulk and just choosing, I'm setting the mu, the red parameter to 0 and keeping only the blue parameter. After a few lines of computation, you can then show up to prefactor. This correlation reduces to something very simple, which is just a moment p of just this total mass of the GMC, the Gaussian multiplicative chaos measure, on the unit circle. Right? There's no more like an area measure because we've set mu to 0, the red one to 0. We only have the blue left. So the functional just reduces to this. And then you can show by importing to probability some of the tools from CFT this result, that you have an exact formula for these moments that was predicted in physics by Fyodorov and Bouchot. And maybe you would like I can say a more probabilistic way to say this theorem is that you're actually just giving the law of the total mass of the GMC on the unit circle. And this law up to constant is just exponential random variable to some power. Now I'm just, in the next 2 slides, now I'm going to generalize this. The first generalization is I'm still on this slide, I'm still working with the mu equals 0, the red constant is 0, so still just the functional, you can compute it, would still just be involves the boundary GMC. But here now we're adding more points. So you should look at this picture. We've solved the bulk 1 point in the previous slide. Now we're going to solve bulk boundary, boundary 2 point, boundary 3 point. And we have full generality for these parameters. And in the mu parameters in blue, get also chosen to be, as I said, piecewise constant on the boundary between the different arcs. So we have exact formulas for these. So these 3 quantities, they're a bit complicated, so I didn't write them. But I can emphasize one thing is that they also give probabilistic information. For instance, a special case of the boundary 3 point would tell you this time what is the law of the mass of GMC on the unit interval, which we actually proved before doing this more general case. We actually proved this in earlier work with Tunan. Okay, and now the next slide is what we generalize further to the case where the mu is positive. So the red mu, which contains the area measure potential, is now positive. We still have the same picture. And in these 2 sets of work in progress, which I hope will be finished pretty soon, we'll be able to solve every correlation function here in this generality on this picture. So I want to say here, I have to make one comment on the proof strategy, which is in this first, for these first 2 correlations, we're going to prove them using, so Morris and Shin really had some amazing insights of applying some of the tools they're expert on, the SLE and the quantum zipper, to solve these correlation function, right? And so now in a joint work with them, we're going to produce formulas for this these 2 correlation functions. And I should say, so this bulk 1 point in the case where the red mu is positive, this one was out of reach using just the probabilistic Liouville CFT tools. And then now building on this and with some of the other techniques, then we can solve the remaining ones. The application, the probabilistic, one of the application of these formulas is when you have both the potentials, it's going to give you some information about the joint law of the area and boundary GMC measures, right? Not just a law of the boundary. Okay. And then let's see, I have maybe 1 more minute. Let me say some outlook and perspective of this work. So, right, so I guess the punchline so far is we've solved in the most generality all these correlation functions. So one thing is we establish a connection between two types of integrability, in a sense, in this field. One coming from the Liouville conformal field theory side, and the other one, thanks to the insights of Morris and Shin on this SLE and quantum zipper side. And I think they have many more works in progress with other co-authors to develop, to push to the limit, really, this SLE integrability. So I think this, really interesting. It's something, this connection people kind of had on their mind for a while, but it was not quite pinned down until very recently. The other thing is I've been doing some work with Promit, Shin, and Yi on the conformal blocks of Liouville theory. So it's, for physicists, it's really the most important object in, well, it's giving you solvability of conformal field theory. And in the work we posted earlier this year, we had to use the exact formula for the boundary 2 point in some place in our proof strategy. So this really has applications to this work. And these conformal blocks, they have some conjectured modular transformation properties we're now working on, which are related. There's some modular kernel that's also related to this boundary 3 point. So it has applications there. And the last comment I want to make is that natural question would be, okay, what if you want to do more points? So the reason you see here, the most points we have is bulk boundary or boundary 3 points, because this is the number of points that fixes Mobius maps of the disk. But if you want to do more, then you have to do a procedure that's called the conformal bootstrap. Or if you want to do higher genus, like an annulus, you'll also have to do this. And this has been solved very recently in the case of the Riemann sphere by a work by Guillaume, and Rod Vargas. And with Shin and Morris in the future work, later in the future, we also hope to do this in the case of domain with boundary. Okay, I guess I'll stop here.
Okay, so we're gonna thank all the speakers from the first session after everybody goes. So hold your applauses for Guillaume for now. So I'm gonna stop the recording.